Good afternoon. Greetings from Halifax, Nova Scotia, Canada. First, I'd like to thank the organizers for putting together a fantastic historical and scientific program and for gathering together a great group of colleagues. I'm sorry I can't be there with you today, but I hope this electronic presentation will do the job. My choice of title for this talk will be obvious by the end. I've been working on density functional theory for about 45 years, and that's pretty much a lifetime. So let's begin at the beginning with my graduate student years from 1975 to 1981. I was a graduate student in the nuclear theory group at McMaster University. My supervisor was Don Sprung. Don Sprung is not very well known in the chemistry community, and that's why a lot of my chemistry colleagues wonder where I came from. Well, I came from a nuclear theory group. Turns out that nuclear theorists do Hartree-Fock theory, density functional theory, as well as chemists. They have their LDAs and their GGAs and their density matrix expansions, and that's how I got introduced to this subject area. But internucleon interactions are a mess, and you can't really do very much in the way of quantitative computational predictions in nuclear theory. So I wandered away from nuclear structure and started reading electronic structure books. Don Sprung was Dean of Science at the time, so I was basically self-supervised and I could do pretty much anything I wanted. So I read the electronic structure books of this man, John C. Slater. John Slater wrote an awesome 4-volume set of books on the quantum theory of atomic structure, molecular structure, and solid state structure. I read all 4, but I was really impressed by the last of these books, The Self-Consistent Field for Molecules and Solids. This book was about the Hartree-Fock-Slater, also known as the X-alpha exchange model, and a curiously named muffin tin numerical methodology for implementing it in solids and in molecules. And this work was done with Keith Johnson. So let me give some context on what was going on in quantum and computational chemistry during my graduate student years. Around 1975, computational chemists were routinely using something called Hartree-Fock theory, where the total energy is equal to a sum of the classical kinetic energy, the classical potential energy, and an exchange energy term, which is related to the occupied orbitals by this somewhat complicated expression. In molecules, Hartree-Fock technology had been well developed in order to implement this Hartree-Fock theory, but it was impossible to apply Hartree-Fock theory in solids, and this is still quite challenging today in solids. In the Hartree-Fock-Slater model, which was actually proposed by Slater in the early 1950s, the exchange energy is approximated in terms of the total spin densities, rho up and rho down, by this expression. This expression is much simpler indeed, and this expression, Hartree-Fock-Slater, is the precursor of modern density functional theory. Furthermore, Hartree-Fock theory was famously unsuccessful at predicting molecular bond energies. Bond energies were generally much too low. Some molecules, like the fluorine molecule, aren't even bound at the Hartree-Fock level. The Hartree-Fock energy of the molecule is higher than the Hartree-Fock energy of 2 fluorine atoms. I'll show you some statistical numbers much later in the talk. Therefore, in addition to Hartree-Fock, one has to compute costly correlation corrections, the most useful being MP2, Muller-Plesset second-order perturbation theory. And thus began my decades-long obsession with computing bond energies. It just didn't seem right that it was so hard to compute something as germane to chemistry as a bond strength. Okay, so what about the Hartree-Fock-Slater exchange model? It turned out that Hartree-Fock-Slater outperforms Hartree-Fock at substantially reduced cost, but unfortunately the performance was erratic. In other words, sometimes bond energies were too high, sometimes bond energies were too low, and the errors were much too large for quantum chemists. Also, the muffin tin computational scheme was intriguing, but again, the errors were much too large for quantum chemistry. So for my PhD thesis, I worked on new computational methodologies in order to implement Hartree-Fock-Slater in molecules. I fixed the inaccuracies of the muffin tin approach by creating a fully numerical, grid-based code for diatomic molecules, which was unique in the world. Other people were also working on improved computational strategies. Everett Jan Behrens was writing code using Slater-type orbital basis sets, and Brett Dunlap was creating codes using Gaussian-type orbital basis sets, and there were others. I eventually produced a self-supervised thesis in 1981 on accurate, fully numerical, grid-based Hartree-Fock-Slater calculations on diatomic molecules. And I have to say, I got absolutely invaluable help from Tom Ziegler, who was a postdoctoral fellow in the chemistry department at McMaster at the time that I was a graduate student there. Without Tom Ziegler's assistance and advice, he taught me the difference between density functionals and spin density functionals. I don't think this thesis would have been completed. So these calculations were the most accurate at the time. I was able to assess Hartree-Fock-Slater without computational errors, but it turned out to be a dead end because the erratic performance of Hartree-Fock-Slater, sometimes overbinding, sometimes underbinding, left no handle on how to systematically improve it. 2 years after I defended my PhD, and as a disciple of Slater, I attended the NATO ASI Advanced Study Institute on density functional methods in physics in Alcobendas, Portugal in 1983. This was a fantastic 2-week meeting organized by Rainer Dreitzler and Hardy Gross. This is where I first met Walter Kohn, Mel Levy, Bob Parr, John Perdue, Andreas Savine, Ulf von Barth, and others, and I hope I haven't forgotten any of my fellow speakers. This meeting was an eye-opener. It taught me that Hartree-Fock-Slater is a model. It's not a theory. For example, where exactly was correlation in Hartree-Fock-Slater? And curiously, Slater's name wasn't mentioned during this meeting, not even once. So subsequently, I made the effort to understand the papers of Walter Kohn. Here are the classic papers of Hohenberg and Kohn, and of Kohn and Sham. These papers laid the foundation for what we now call density functional theory. I left the Slater School after that meeting and started working in the framework of modern Kohn-Sham density functional theory. The first approximation in Kohn-Sham density functional theory is known as the local density approximation, LDA for short, for the exchange plus correlation energy. The local density approximation for the exchange correlation energy integrates over all points in the system the exchange correlation energy density of a uniform electron gas having the local values of the up and the down spin densities. The exchange part is essentially Hartree-Fock-Slater. The correlation part is a lot more complicated, and I really won't say anything about that. I published LDA results for diatomic molecules that I had computed with my fully numerical grid-based code in 1986 and noted that the LDA is overbinding as opposed to the underbinding of Hartree-Fock. Here is a table from that paper. You can clearly see that the binding energy or dissociation energy of the LDA is too large for every molecule in this table except the lithium molecule, which is underbound by 0.1 electron volts. After that, I worked on corrections to the exchange correlation LDA, which depend on density gradients. John Purdue has coined the name generalized gradient approximations, or GGAs, for these things. So here is the exchange correlation LDA, which I showed you previously. And here's the general expression for an exchange correlation generalized gradient approximation. It depends at every integration point in the system on an exchange correlation integrand, which depends on the up and the down spin densities, but also the up and the down spin density gradients. Others too were working on GGAs. David Langreth, of course, John Purdue, Li Yang, and Parr. And this turned out to be very successful research. Personally, I published 3 GGAs for exchange energy, now known as B86, B86b, and B88, which were able to reproduce the exact Hartree-Fock exchange energies of atoms with remarkable precision. In the B86 paper, I discovered that diatomic bond energies were significantly improved by using an exchange GGA rather than just the local density approximation. And here's the reference for that paper. This paper, I think, really gave the first hint that DFT might be useful in quantum chemistry. Indeed, Tom Ziegler picked up on this immediately, and for a period of about 5 years, he was a powerhouse computational chemist, applying GGAs to problems in inorganic chemistry and especially organometallic chemistry, which is a field in which other computational chemists could do very little. But Tom Ziegler nailed it by applying GGAs in organometallic chemistry. He was so good at this, he actually wrote a review article, there it is, 1991, on density functional theory as a practical tool in quantum chemistry. Here is my last and favorite exchange GGA, B88. You can see that it has a fairly simple functional form and only one parameter, B, which is fit to the exact Hartree-Fock exchange energies of inert gas atoms. B88 reproduces exact atomic Hartree-Fock exchange energies of atoms better than any previous exchange GGA or any GGA that followed. Here is a table of exchange energies for first and second row atoms. You can see clearly that the LDA always falls short with a relative error of something like 5 to 10%. B88, on the other hand, gives excellent atomic exchange energies compared to exact Hartree-Fock, especially here through the second row. The errors are typically 0.1 to 0.3%, which is really quite excellent. Also, beginning around 1988, I developed new grid-based, fully numerical methodologies for polyatomic molecules, which previously I could only do for diatomic molecules. I called this the NUMOL program, numerical molecules. And this was worked out in a series of 4 papers in the period 88 to 90. First, a paper on numerical integration in polyatomic molecules, numerical solution of Poisson's equation in polyatomic molecules in order to get the Coulomb potential, numerical solution of Schrodinger's equation in polyatomic molecules, and then I put it all together in this paper, and that constitutes a complete DFT numerical program. I've highlighted this paper because this integration scheme, or some small variation of it, is the backbone of just about every DFT program in the world today. So finally, I could go beyond diatomic molecules to general polyatomic molecules, and I could do it without the need for any basis sets whatsoever. This was my first application of the NUMOL program to the test set of 55 accurate experimental atomization energy benchmarks, where atomization energy is the sum of all the bond energies in a molecule. And this test set was known as the G2 thermochemical test set of Curtis, Raghavachari, Trucks, and John Popel. They compiled this test set in order to assess a theory they had created known as Gaussian 2 theory, which is a multi-step composite wave function procedure involving Hartree-Fock, MP2, MP4, and QCI correlation calculations in a variety of basis sets. It was the most accurate thermochemical procedure at the time, but still very, very costly. It was practical, but it was costly. The mean absolute error, and I'll be calling this MAE throughout this talk, on the 55 G2 atomization energies was 1.2 kcals per mole, which is really very respectably small. So when I ran a NUMOL on this G2 thermochemical test set, I found that the MAE of the local density approximation was 36.2 kcals per mole, which is huge and most definitely unacceptably large. However, when I added the B88 exchange gradient correction to the LDA, the MAE was reduced to 3.7 kcals per mole, which is about 10 times smaller than the mean absolute error of the LDA. This was pretty impressive, given how rapid these calculations are. So this begs the obvious question. Given that Hartree-Fock is massively underbinding, and that G2 theory is much more costly, how does this very simple GGA approach achieve such an excellent result? Well, the answer is in this box, and I don't have time to explain the details. I'll just run through this very quickly with you. LDA and GGA exchange and correlation energies depend at every integration point on local quantities, the local density and the local density gradient. This inherently mimics left-right or non-dynamical correlation. Now, I can't explain this to you, but this kind of correlation is an electronic correlation between electrons on different atoms in a molecule. There's another kind of correlation which we call dynamical, which occurs between electrons on the same atom. So this inherent mimicking of left-right correlation in LDA and GGAs is the secret to the success of GGA approximations. Actually, Slater knew this when he first proposed Hartree-Fock-Slater in the early 1950s. And there's a much more recent and very detailed and interesting analysis of how GGAs mimic left-right or non-dynamical correlation in this paper by Nick Handy and Aaron Cohen. I presented these results at a very memorable meeting. The 1991 International Congress on Quantum Chemistry in Menton, France. This was quite a week for me personally and for DFT. I was awarded the 1991 International Academy of Quantum Molecular Science Medal for researchers under the age of 40. I reported for the first time my DFT GGA test results on the G2 atomization energies, and I had a long 5-course lunch conversation, the first of many conversations I would have, with Sir John Popel, the grandfather of computational chemistry and the senior author of G2 theory. As I said, it was a long conversation and we talked about many things, but he had two major concerns. First, DFT papers tended not to report total energies. Traditional quantum chemists always reported total energies. He felt this would be very helpful if we would do so. I suggested that the reason was DFT's origin in condensed matter physics, where total energy is much less important. He also wondered about this technical problem. What about the grids, namely the integration grids? And on that subject, I referred him to my 1988 numerical integration paper. On the last day of the conference, John Popel delivered the closing plenary lecture. Its focus was G2 theory and the G2 test set. However, largely prompted by my talk, which I had given the day before, he spent almost 10 minutes of his talk addressing his thoughts about DFT. This was a historic moment for density functional theory. And if you don't believe me, I have the video. Within a year of the 1991 Monton ICQC came the turning point for DFT. In these two 1992 papers, Peter Gill, Benny Johnson, John Popel, and Mike Frisch introduced an exchange correlation GGA B88LYP, or as it is more commonly known, just BLYP. It's a combination of the B88 exchange GGA and the Li, Yang, and Parr dynamical correlation GGA. Dynamical correlation GGAs actually have little effect on molecular bond energies. It's the exchange GGA that really matters. Also, they created a new release of the Gaussian program, Gaussian 92/DFT. The Gaussian program is ubiquitous in chemistry. It's just about in every chemistry lab, let alone every theoretical chemistry lab. So mainstream quantum chemists finally paid attention to DFT, and every chemist could do DFT computations. That's a scary thought. Interestingly, as John Popel had wanted in our lunch conversation the year before, they reported total atomic energies in these papers, and they actually got very good agreement between BLIP and experiment for atoms with atomic number less than or equal to 10, that is below neon. In fact, these total atomic energies were better than 10 millihartries in agreement with experiment in every case. Their G2 atomization energy, MAE, turned out to be very similar to mine, and they additionally reported good ionization potentials, electron affinities, and proton affinities. These are also in the G2 test set, in addition to the atomization energies that I had focused on. The next year, 1993, came another big moment for density functional theory, the invention of hybrid functionals. In a hybrid functional, one mixes in a small fraction of exact Hartree-Fock exchange with the GGA exchange. And this is justified theoretically by the coupling strength integration formula, also known as the adiabatic connection formula, for the density functional theory exchange correlation energy. This is a very busy slide, but let's work our way through it. In cone-sham DFT, the exchange correlation energy is rigorously given by this formula, which I think is the most important formula in all of cone-sham density functional theory. This is the adiabatic connection or coupling strength integration formula. It involves an integral over a coupling strength parameter, lambda, that switches on the Coulomb repulsions between electrons. U, exchange correlation at lambda in this formula, is the potential energy of exchange correlation at coupling strength lambda. And here are the authors who originated this very important formula a very long time ago. At lambda equals 1, the system is fully correlated. At lambda equals 0, the system is completely uncorrelated. And we have essentially exact Hartree-Fock exchange. Now recall that the LDA or GGA exchange approximations are inherently correlated with left-right or non-dynamical correlation. And you can't turn that off at any value of lambda. However, at lambda equals 0, there should be absolutely no correlation. So how do you fix that problem? This is the functional I actually published in my 1993 paper known as B3PW91. It was later lipified by Mike Frisch. PW91 is another dynamical correlation GGA due to Perdue and Wang. And this is the LYP dynamical correlation GGA that I mentioned before. So what you do in order to fix this problem at lambda equals 0 is you swap out some exchange LDA and you replace it with exactly computed Hartree-Fock exchange. And when you do that, you better also readjust the GGA correction of B88 for exchange and of PW91 for dynamical correlation. So we have 3 parameters altogether, and there are their values as fit to 56 atomization energies, 42 ionization potentials, 8 proton affinities, and also 10 first row total atomic energies. We obtained an atomization energy mean absolute error of 2.4 kcals per mole compared to 1.2 for G2 theory on the atomization energy test set. So this is significantly better than the 3.7 kcals per mole that I had obtained before with a pure GGA. However, B3PW91 crossed a line. Previously, GGAs had 1 or 2 parameters fit to atomic data only. Unfortunately, the exchange mixing fraction in hybrid functionals is intimately related to multi-center effects in molecules and cannot be determined by atomic data alone. Fitting to molecular data is necessary. Not everyone liked this idea. Notice the date of DFT's death in the title. Unfortunately, I was about to make things even worse. In this paper in 1997, I proposed a method for systematic generation of exchange correlation GGAs by series expansions fit to benchmark data. This functional, B97, was fit to the same data as B3PW91, 56 atomization energies, 42 ionization potentials, 8 proton affinities, and 10 first row total atomic energies. Now, when you do this kind of thing, overfitting to the data is a real danger. So I carefully looked for signs of overfitting as expansion order was increased, things like oscillations in the resulting series expansions. And I conservatively settled on 3 terms, or a quadratic series, for each of exchange and same spin and opposite spin dynamical correlation. For a total of 10 linear parameters altogether, that's 3 parameters for each of the 3 series and an exchange mixing fraction. So in B97, I obtained an atomization energy MAE on the G2 atomization energies of 1.8 kcals per mole, compared to 2.4 for B3PW91, and remember 1.2 for G2 theory. That's pretty good. Notwithstanding, however, that this is, after all, a 10-parameter fit. I did even better the following year with B98, a second-order GGA, namely involving the Laplacian of the density, but I won't discuss that here. It was not my intention with the B97 paper to suggest that series expansions should replace good theory. I simply wanted to demonstrate that the hybrid DFT approximations of the time were near optimum, even if we went from 3 to 10 parameters. Some researchers, however, went much further with parameter counts. They compiled increasingly large sets of benchmark data, and they fit them with as many as 50 parameters, which I think is the record. I won't name names, but my fellow speakers know who I'm talking about. There even appeared in Chemical and Chemical Engineering News an interesting article on this circus in 2008. I'm sure Martin Hedgorden has much more to say about this in his talk, but let me say a little bit in mine. In a series of papers, their B97 and Omega B97 series in the years 2014 to 2018, Martirosyan and Martin Hedgorden put an end, or at least I hope they put an end, to this parameter craziness with carefully crafted studies of series expansion spaces for a variety of DFT and hybrid DFT methods. What they did was fancy fitting and transferability analyses, and they concluded that only a dozen or so parameters is generally optimum, not 50, consistent with the 10 parameters in B97. Here are their landmark papers: Omega B97 XV, which is a GGA that resulted from this work; Omega B97 MV, which is a so-called meta-GGA; and Omega B97 M2, a double hybrid functional, and I'll talk about double hybrids a little later. Now, let's move on to another issue. The simplest problem in quantum chemistry has been a huge embarrassment for GGAs and hybrid functionals since their beginning. H2+, just one electron split over two hydrogen nuclei. In this case, it's Hartree-Fock that gives the correct potential energy curve for H2+. But look what happens with B-lip and B3-lip. They produce enormously incorrect asymptotes, almost as deep as the energy minimum itself. This is a problem density functional theorists call self-interaction error, and this is a big problem in DFT. I actually think a better term is localization, delocalization error. It's much more descriptive. Now, I don't have the time to explain this, but in a nutshell, when exchange and correlation effects extend over two or more centers, as is the case when one electron is split between two hydrogen nuclei and then you pull those nuclei apart, GGAs are simply not far-sighted enough. GGAs are short-sighted, and that's the origin of self-interaction error. Let's be honest, though. Who really cares about H2+? Well, the same problem manifests itself, but to a lesser degree, in all stretched or delocalized odd electron systems. So we can expect problems in the transition states of radical reactions with GGAs and hybrid functionals, or in highly delocalized organic radicals, and probably in other situations, which I haven't listed here. This problem had to be fixed. It was a huge embarrassment. John Popel became aware of this problem the moment he touched density functional theory. The only option, despite the remarkable simplicity and success of GGAs, was to abandon GGA exchange approximations and the hybrids that use them and go back to computing exchange exactly, whether we like it or not. That, in part, explains my title, Full Circle. My journey took me from Hartree-Fock to exchange GGAs and, as I will now show you, back to Hartree-Fock. In 2005, I published a post-Hartree-Fock non-dynamical plus dynamical DFT correlation model that I had been working on for about 3 years. The leading term in the exchange correlation energy is exact Hartree-Fock exchange, no GGA exchange whatsoever. That is followed by 2 non-dynamical correlation terms, both based on a real space density functional model, one for opposite spin, one for parallel spin, and then we follow with 2 dynamical correlation terms, one for opposite spin and one for parallel spin. The 4 linear fit coefficients in this paper were fine-tuned to benchmark data like the G2 or the subsequent G3 atomization energies. And what I mean by fine-tuning here is that this is not the same kind of fit that I had embarked on previously. Theory alone dictates that these linear coefficients should be about 0.5, that comes from the virial theorem, and that these coefficients should be about 1. And indeed, the fit does return expansion coefficients that are very close to these theoretical values. And even if you use these theoretical values, one obtains a very decent functional. So this theory is now known as BO5. Let me just say that the non-dynamical correlation part was extremely difficult to model with a density functional, but we succeeded. The dynamical correlation part comes from a 1988 paper on dynamical correlation that I had published. 1988 was a very good year for me. Numerical integration, B88 for exchange, and also this 1988 dynamical correlation functional. It works as well, or even slightly better, than hybrid functionals, including B97. So let me show you some numbers. Here is a table of mean errors and mean absolute errors on the G297 extended G2 test set. This test set contains 148 experimental molecular enthalpies of formation. And enthalpy of formation is related to atomization energy, so we're essentially looking at atomization energies here. I told you a while back that Hartree-Fock is massively underbinding with an MAE of 158.9 kcals per mole. Hartree-Fock-Slater is somewhat better, 35.0 kcals per mole, but still not good enough for chemists. The exchange correlation LDA is massively overbinding with an MAE of 82.9 kcals per mole. Here is a pure exchange correlation GGA containing B88 and the PBE, Purdue Burke Ernzerhof dynamical correlation GGA from 1996. I decided to use this functional instead of the older PW91 when I compiled the data in this table. The MAE of this pure GGA is 8.1 kcals per mole. The corresponding hybrid functional B3PBE does significantly better, reduces the MAE from 8.1 to 3.2, which is significant. BO5 is even slightly better at 2.6 kilocalories per mole. The mean absolute error of G2 theory on this extended G297 test set is 1.6 kcals per mole. So we're not too far away with BO5, 2.6, as opposed to G2 theory at 1.6 kcals per mole. BO5 is a very complicated functional of local spin densities, local spin density gradients, including the Laplacian and the kinetic energy density, and this somewhat problematic ingredient. BO5 needs the Coulomb potential of the exact Hartree-Fock exchange hole at every grid point in the system, and that is given by this rather complicated expression. Unfortunately, this isn't available in most quantum chemistry programs, and so BO5 isn't in fact used by very many people. But it does correctly dissociate all of these two-center 1, 2, 3, and 4 electron molecules and ions. H2 plus, as we've already seen, but also helium 2 plus, are huge embarrassments for any GGA or hybrid DFT. BO5 correctly dissociates them all. And it gives much better reaction, barrier heights, and organic radical energies than hybrid functionals. Now, on to something else. Around 2005, standard density functionals did not incorporate non-covalent dispersion interactions. Without dispersion, DFT was doomed. It was touted as a tool for computations on large systems. That was its purpose. But the large systems of interest in biochemistry, biology, surface science, molecular crystals, etc., were dominated by non-covalent dispersion interactions. Some empirical dispersion corrections had been tried, but they weren't satisfactory. What we needed was good theories of dispersion. Beginning around 2005, I developed with Aaron Johnson a non-empirical dispersion scheme based on an interesting model. This represents an electron at position Ra in a spherical atom A, and the arrow points to the center of charge of its associated exchange hole, and similarly for an electron at Rb in atom B. Now, an electron plus its exchange hole is a neutral entity overall, but generally the exchange hole is not centered on the electron unless it's at the nucleus. And so the electron plus its exchange hole is a neutral entity that has non-zero multipole moments, and we allow these to interact with the multipole moments of an electron and its exchange hole at Rb. Put this multipole interaction into second-order perturbation theory in the closure approximation, integrate over all points in A and B, and we get the asymptotic dispersion series with non-empirical expressions for the dispersion coefficients. This was a novel, even controversial dispersion model. We call it XDM, the exchange hole dipole moment dispersion model, and I'll let Aaron Johnson say much more about it. After about 2000, benchmark data sets began to multiply as ever-increasing numbers of functionals needed fitting and calibration. There were the G2, G3, etc. test sets from Popel and others, S22, S66, and other non-covalent interactions test sets from Hochsche and others. We, Aaron Johnson, Felix Kahneman, and myself had our own dispersion test sets. Don Trular compiled diverse reaction energies and barrier heights in some very useful test sets. There's the large main group chemistry test set of Marty Rossian and Martin Hedgordon. And from Lars Gehrig and Stefan Grimme, main group chemistry test sets GMTKN24, GMTKN30, and GMTKN55, the general main group thermochemistry kinetics and non-covalent interactions chemical database of Lars Gehrig, Stefan Grimme, and other authors. This is a compilation of high-level wave function reference data from over 50 literature sources for over 1,500 reaction energies and barrier heights covering a wide range of main group and organic chemistry. It's organized into 5 reaction categories containing 55 subsets altogether. Let me go through them rather quickly, and I will highlight some of the more challenging subsets. Basic properties and reaction energies of small systems, and notice that this includes a self-interaction error test set, SIE 4x4. Reaction energies for large systems and isomerizations, and this includes a particularly challenging test set called mindless benchmarking, as Stefan has named it. This is about decomposition energies of randomly created artificial molecules. It's a very challenging test set of the robustness of density functionals. Reaction barrier heights, and a large number of test sets for non-covalent interactions. These are the intermolecular non-covalent interactions subsets, and also intramolecular non-covalent interactions subsets. The quality of a theory is usually assessed by calculating the weighted total mean absolute deviation from the reference data. The WTMAD2, which replaces an earlier WTMAD1. This is a weighted mean absolute deviation in which the 55 subsets are weighted according to their average reaction energies in order to balance their importance in the WTMAD. In other words, the rare gas interactions are as important in the WTMAD2 as the atomization reactions. Thanks to COVID lockdowns, I had the time to set up GMTKN55 for least squares fitting and WTMAD2 calculations. In 2022, I published 2 hybrid functionals that used BO5 non-dynamical correlation. B22, a combination of essentially BO5 plus XDM dispersion, and B22 plus, a combination of BO5 plus B98 series expansions plus XDM dispersion. Their WTMAD2s are for B22 and 7 linear parameters, 3.3 kcals per mole. B22 plus performs somewhat better at 2.8 kcals per mole, but with somewhat more parameters, 18 linear parameters. Compare these with the best previous hybrid in the literature, omega B97MV from Marty Rossian and Head Gordon. With 12 linear parameters, it has a WTMAD2 of 3.3 kcals per mole. So we do a little bit better with these functionals, but remember, these are based on that rather complicated BO5 non-dynamical correlation model. In 2023, Jan Martin at the Weizmann Institute encouraged me to add MP2-like second-order perturbation theory terms, more often called PT2 in the context of density functional theory, to B22 and B22+. These are called double hybrid functionals, and recent advances in resolution of the identity MP2 technology have made them very cost efficient. Double hybrids have been popularized by Stefan Grimme, beginning in this 2006 paper. Stefan advocated using density functional theory orbitals in the PT2 part instead of Hartree-Fock orbitals, as had been used in traditional MP2 theory. Thus, after some 40 years of preaching that we should use occupied orbitals only in cone-sham DFT, I started experimenting with double hybrids, which use unoccupied virtual orbitals as well as the occupied orbitals. I was amazed by the results. I published 3 papers on double hybrids in 2023 and 2024, DH23, Rev DH23, DH24, and I consider DH24 to be the best of them. In my studies of double hybrids, I came across a pleasant surprise. It turned out that the complicated BO5 non-dynamical correlation terms were not necessary in the presence of PT2 correlation. PT2 correlation essentially replaces them. All three double hybrids have this general form, and I really don't have the time to say anything about that. They have 12 linear parameters fit to GMTKN55. I use B1 lip orbitals, and I use a rather good basis set, DEF2 QZVPP, with diffuse functions when necessary. This is an important point. All the terms in that DH formula that I showed you on the previous slide are motivated by what I believe to be good local physics and good underlying physical models. Indeed, I arrived at DH24 directly, logically, and straightforwardly in only about 18 months of double hybrid work. How well do these double hybrids perform? Let's have a look at some WTMAD2 values for DHs and a couple of functionals. Omega B97M2, I've mentioned this before, from Martyrossian and Head-Gordon. This has 14 linear parameters. It is generally considered to be one of the very best double hybrids in the literature. Its WTMAD2 is 2.13. XYG8 from the group of Jan Martin has 8 linear parameters, 1.85. DH23, 12 linear parameters, 1.76. Rev DH23, 12 parameters, 1.73. And DH24 with 12 linear parameters, 1.72. To the best of my knowledge, this is the lowest WTMAD2 in the literature at present for any hybrid or double hybrid functional. And this is especially for Stefan Grimme. The DH24 mean absolute errors on the self-interaction error and the mindless benchmarking subsets are 2.04 kcals per mole and 546 kcals per mole. These are among the very best in the literature, which implies that DH24 is robust and physically well-based. I never ever thought I'd be at the top of John Perdue's Jacob's Ladder, but there I am with DH24. That figure was taken from this paper by Jan Martin and Golokesh Santra. I have concerns about double hybrids. The number of published DHs is exploding. Also, double hybrids that are outstanding in main group chemistry usually have a high amount of Hartree-Fock exchange. DH24, for example, is 81.1% Hartree-Fock exchange. This is probably too high for transition metal chemistry, where DHs would prefer to have something like 50% exact Hartree-Fock exchange. So tread carefully. So where are we now? The group of Jan Martin has looked at triple hybrids, and I believe Martin Head-Gordon's group has also looked at this kind of functional. These contain density functional theory terms, Hartree-Fock, PT2, and PT3. In this paper, these authors obtained an incredibly low WTMAD2 of order 1.2 kcals per mole with several functionals by adding a PT3 term, computed with hybrid orbitals containing 40 to 45% Hartree-Fock exchange. This is in the realm of composite procedures such as G2, G3, and G4 theory. So let me speculate that the end of DFT and wave function theory hybridization may have been reached. However, PT3 is not computationally practical at present. That could change. And that brings us to my last slide. In our quest for robust and universal combined DFT-WFT methods, I think we really have come full circle. GGAs, hybrids, double hybrids, perhaps triple hybrids, and yet all of these have their appropriate places in computational science. Pure GGAs, for example, will be the workhorse of condensed matter theory and computations on very large systems for a long time. And that's the end of my talk. Thank you for listening.